Everybody is now a movie maker. Anybody in this class can take your iPhone and let's say you have an account with Google, which half of you or more than that do. So you get on YouTube, and on YouTube you sign in with your Google ID, and then there's this little video camera up there in the upper right hand corner, and you press that video camera and it says, what would you like to upload? And you go, oh, well, I have some videos of my kids. I'd like to upload that. So you press the upload button, and if you follow the instructions, within a few minutes, that video is preserved for posterity on YouTube. You have become a filmmaker. And I did that. I became a filmmaker, and this class is obviously being uploaded to the web after this. But this lady, she has 38 followers. 38. In the world of 380,000 followers, she has practically no followers. I have also practically no followers at 267 this week. Not followers, subscribers. So I'm going to play you a bit of this woman's video. I think it's very entertaining and says a lot about the things we're talking about in this class. So with no further ado, let's see what I can play.
If you were to make a map of space, what would it look like? This? This? Or maybe this? All of these images were released on April 25th by GAIA, the European Space Agency's mission that aims to chart 3D models of our galaxy. As a result, they've created the largest 3D star atlas our world has ever seen. Looking at it, you'll find planets, moons, asteroids, comets, and 1.7 billion stars. That's 700 million more celestial bodies than the catalog had in 2016 when GAIA first posted it. The Galactic Census, as they call it, was drawn after 22 months of sky charting with a 1 billion pixel camera and 2 telescopes that can see beyond our own Milky Way galaxy. This involves an insane amount of precision. In the ESA press release, it was equated to human eyes spotting a coin lying on the surface of the moon. If that sounds impossible, that's because it is. But this intergalactic guide has ventured beyond the realm of what astronomers thought was feasible. According to GAIA scientist Anthony Brown, it's a huge leap forward. Let's take a closer look. You might recognize this image if you've ever seen the Milky Way on a clear night. From Earth, it looks like a bright band that stretches across the sky. But GAIA's map gives you the ability to zoom. And if you've never seen the Milky Way in person, well, if you have a computer, now you have the power to scroll across 100,000 light years of data. That glowing band of light across the middle is the galactic plane, a flattened disk where most of our celestial neighborhood is found. As you can probably imagine, the bright regions indicate the denser concentrations of bright stars, and the dark regions display areas with less. The 2 bright areas in the lower right are Magellanic Clouds, 2 dwarf galaxies that orbit the Milky Way. Other areas show groupings of stars held together by gravity. Sometimes these are globular clusters, but sometimes they show other galaxies, which give us a glimpse into places that might contain solar systems beyond our own. These are known as extrasolar regions, and they've been especially helpful in progressing the field of astrobiology in the past 25 years. That's part of the reason why this catalog is so important. It provides more information than we've ever had before when it comes to understanding the motion and composition of the universe beyond our planet. Astronomers can use it to study how the cosmos moves, hypothesize how the galaxy formed, and search for new planets. It's also found 14,000 asteroids, which helps astronomers track their trajectory.
So I'm going to stop it there.
That was good.
That was good, right? So what is her claim to fame? None. She doesn't even say the word globular clusters correctly. She says globular clusters. So she actually obviously has no contact with the astronomical world. She just loves it, right? Just like anybody else in this room. Just loves it, except that she's probably in her early 30s, and this is her hobby, making this movie. So anybody can make a movie, and that includes me. So thank you. and I posted on her website that I was going to do this. So hopefully, and she has 8 comments, so I'm one of her 8 comments. So the chances are she actually will see this. Thank you very much. Thank you. Appreciate it.
Do you remember her name?
I don't remember her name, but yes, I do. Her name, of course, I can't remember her name. Her name is Emma Bianca, and she has 49 subscribers. It says it right there.
Oh, okay.
Okay?
Yeah, it's in the way.
Right.
Not on the
I'm
way.
in the way. I know that.
Right.
I know that.
Okay, Emma Bianca.
So it's a pretty nice film for like an amateur, right? Because all that stuff that she's got, I've seen all that stuff and lived piece after piece. She pieced it together. She voiced over it. She wrote the script. You know,
It might be a job application because she's pretty good at writing and piecing together and making it very understandable and interesting. I mean, she's...
Well, I've seen a lot of job applications on the web these days. There's a
Right.
website called TikTok,
Uh-huh.
and these people do 20-second videos of themselves,
Right.
and they are completely nobodies, but because what they do is interesting in 20 seconds, they end up with millions of followers. And then these people will suddenly become famous one day. There is a person on TV today. Her last name is Singh. She's Indian. She's a comedian. I think it's a little late with so and so Singh, and she is completely a web created person. She invented herself on the web, and she got a TV show as a result. So yeah, job app. If you want to do anything, do a film, become famous. That's your entry into the world.
You have a chance.
I have a chance.
Yes.
I have a chance. That's right. I'm already famous. I've got 267 subscribers.
Because we don't.
And
because
10 more since
we're
last
not
week.
Knowledgeable. You're knowledgeable. You have a chance.
I have a chance.
Laird, may I
Yes.
ask lately,
You may.
how many have way more exoplanets been found lately? I mean, with Sagan and everything. I mean, we're looking for exoplanets, just right, Goldilocks,
Right.
enough like Earth. Has that been burgeoning lately? Have we been finding, we meaning, people who are looking for this stuff, have they been finding a lot more exoplanets? Of course, they're out there. Is there any development looking like, hey, this exoplanet is, could be?
No. I mean, from time to time, when anything surfaces above the level of different, then it makes the New York Times. And the problem is that we are finding exoplanets all the time still, but to find something that is actually now newsworthy, you have to find something that is a little better than everything else that they found. And since they found one of everything more or less, but nothing really, really good, which means that let's say they found 7,000 exoplanets that they have confirmed, and none of them are Earth-like in any way. Because what do you need as an Earth-like? You want it to be around a star like our sun. To go around in a year would be 2 good things. Then it would be an habitable zone where there would be water on the surface. It has to be Earth-sized. So just take 3 parameters. Earth-sized, 1 year around, sun-like planet, sun-like star. They haven't found anything remotely like that. And that's hard to find, because if you look for an Earth-like planet around a sun-like star, it only passes in front of the star to block your view once a year.
Right.
So to confirm, you need 4 years, 3 plus 1, 4 years to be sure that it's not an artifact. And the spacecraft that was designed to do that only lasted 4-ish years. It never got to the 4th year. So there's been no spacecraft looking up at a star that might have an Earth-like planet for 4 years. So that we're not going to find these easily.
No, it's very difficult, yeah. I just wanted- okay.
Yeah. So this is Gaia. This is the data from Gaia. And And over here is, here's the data from Gaia. I have to zoom out again, apparently. Come in. There you go. Okay. Now this, you see, this is the data. I am, like she was doing in the video. How was she doing this in the video? Because she was using this exact display here. Can I make this any bigger? Yes. Okay. So this is the entire sky. Over here, you see these are little island universes. These are clouds in our sky, except they're not in the Milky Way. They are their own galaxies. This is the small, and this is the large Magellanic Cloud. So, but we're not looking there. We're just looking along the Milky Way, and anywhere along this image, I have the ability to zoom in. So I'm going to zoom in. Let's say over here where this purple cross is. So I zoom. And as I zoom, what I want you to see is that more stars appear than there were before in the same image. What happens is some of the stars, see now that went black, because what's happening now is the same image that you were seeing at is being replaced by an image that has more data in that particular spot. So whereas before you saw it looking like that, now that same image looks like that with all those additional stars, points of light showing you now. And so there's 3 levels of zoom here. So I can continue to zoom in. Remember, we'll talk, and there it goes blank again while the data is being filled in. And I'll zoom out again so you can see the difference. This is in, and then out. In, out. So you can see this thing has many, it has 1.7 billion stars. As I zoom in even further, you can see that I don't get better. All I get is pixels. So this is the best picture that I can get with this software that I'm using, which is publicly available. Nevertheless, as we zoom out, now it will become a continuous change. We're going to get the data so we can see a much better idea of what Gaia has done. 1.7 billion stars. And there'll be a few more, maybe 500 million more by the end of next year. So I'm pretty impressed. Here's a trailer. There's software that I can get, which I love to get this sort of stuff. When they released the data, they also released a program to manipulate the data. So I can get data, I can take this data, put it into the program that they have released at the same time, and literally visit all of the Milky Way. And I have my choices. I can have the itty-bitty data set that is good for playing around, just zooming around and having a little bit of fun, at maybe 7 million stars, and maybe 7 megabytes of data. But I can also go for the 7 gigabytes worth of data. I haven't done that, so I'm not going to do that. But what I'm saying is I have the ability to visit the universe and fly through it with data I've never had before. And so are so many other people who simultaneously, when this data was released, 7,000 people or 2,000 people, somewhere in between, downloaded the data and went crazy visiting the universe, visiting the Milky Way. I'm just going to show you this trailer, which was made to advertise the data, the software. So this is just, if you will, coming attractions, what you can do in your own home with the Gaia data. So this is within about 9,000 light years, which is not much. This is what you can see. So I can do all of this without the music, or maybe even with the music, with the software on my computer. So that is a cloud around the sun.
You see that picture of the sun that looks like
The ball of oats that you saw was, in fact, the cloud of asteroids that surrounds our sun at about a light year. So we know it's out there. So we simulated it in this simulation. This, now what is this? Doesn't look like stars. What they've done here is they've said, forget the stars. Let's see what the nearby universe in the Milky Way looks like gas-wise. Let me show you the clouds. So there is Taurus over there. Or here, this one over here was called. This one was called the Orion Nebula. Which one? This one. This one was Orion. Now here I'm stopping it here because in this picture we actually have some another cartoon version of this. Remember, this is not a cartoon version. Oh, of course it is a cartoon version, but it is data that is taken by the Gaia spacecraft, and the clouds are now in the right places with the right size and the right shape. This is the same picture, in a way. We are here. There is the Orion Cygnus arm, which is this is the whole Milky Way, with its spiral arms. There is a Perseus arm that spirals like this, and it's further out. There's a Sagittarius arm, which spirals like this, and it's further in. So what you're seeing in that video is this piece of arm, this piece of arm, and this piece of arm. And of course, it doesn't look so much like a piece of arm. This, even in this picture, you're seeing that this is just little dots of clouds that form along this arm. Dots of clouds which form along this arm, and dots of clouds which form along that arm. So this is not so different in terms of what it's saying than the picture that you were just looking at. So there's the Perseus arm, there's the Orion Spur, and where's the Sagittarius arm? Oh, over there. So there's the Sagittarius arm. Except that this, see, a few years ago, the picture you had was the crappy little drawing that I had. Now, you've lived long enough to see the universe in terms of this is the star forming regions in our neighborhood. These are the stellar nurseries that live near you. Maybe you need to go babysitting, it's just a few thousand light years away, to go visit any of these stellar nurseries and take care of the young stars that are just being born because they don't know how to behave, and you have to take care of them. Many of them will explode because they've done a bad job of forming too big. If you form too big, you blow up. You need to do that. If you want to be conservative and you form small, you can live for 1 trillion years. But so there definitely is need for babysitting services.
So this was made possible by the Gaia discovery?
This was all made possible by the Gaia discovery. Right.
And
Right.
who did she say was responsible for Gaia? I mean,
I mean the person?
well, the group.
The group,
whatever.
the group is called the European Space Agency. Their equivalent of NASA.
Ah, they're the equivalent of NASA. Okay.
Yes.
Okay.
Does every part of the universe have star nurseries, or have we found parts that may not?
That's a good question. Is every part of the universe have stellar nurseries? Or have we found parts that do not? And the answer to that question is I think you're going to find that to be unexpected. What do you think the answer is? What do you think the answer to your question is?
We guess that everything is the same.
You would guess that everything is the same, but the universe is big. And when you say the same, what you need to do is add in everything that is different in order to get the same. So if you just take the Milky Way and you say, I'll use that, and say, is everything like the Milky Way? The answer is no. The Milky Way is not the same as the next door neighbor to the Milky Way and the next door neighbor over there. This Milky Way, for example, has spiral arms. And in the spiral arms, there are star-forming regions. There are galaxies that are 10 times bigger than the Milky Way that don't have spiral arms. And they are not forming stars in that galaxy. Those galaxies have finished their star-forming business and they are old. What?
I meant the entire universe generally has similar things, even if they're not identical. If it all supposedly started at the same instant and went out in every direction, wouldn't there be a lot of similarities in every direction?
Wouldn't it be a lot of similarities in every direction if the universe started at the same time, went off in all directions? Wouldn't the universe be similar? And no, yes, it started at the same time, but various regions got head starts in various ways. For example, let's say that you had a galaxy which formed all by its little ohmsum, and it stood there for the next 13.8 billion years and didn't encounter another galaxy. Then it would have a very different history from these galaxies all together that managed to collide with each other and do amazingly different things with each other, so that that region is completely different from this region, which is just the one little bitty galaxy that never had any friends. So depending upon the history of each galaxy does something different. You can classify them according to how they're different, and there's a range of differences from young to old to spiral to elliptical to irregular. All these different galaxies exist with various reasons and various histories. So they're not the same. Yes, they were formed at the same time, but they survived, and their history is completely different. So some have places where there are no planets that could possibly be terrestrial. For example, there's some stars in our sky. In fact, there's 320 more or less of them. They're not stars, they're just very bright spots in the sky. They're called globular clusters. And each one of those globular clusters has about approaching 1 million stars. Not 400 billion stars like our galaxy, but just 1 million. But it's compact. And it was formed before our own galaxy was formed. So if you will, these are the little babies that have grown up and old and still survive in our galaxy, but they are, if you will, primordial galaxies. And in those primordial galaxies, you find that they differ in their composition from the rest of the galaxy. And the reason is that they ate up all their gas, and they're not making any stars. And so they have very little of the stuff that we are made of inside of their stars. Yes, again.
So, is there the possibility, because all of this is guesswork?
What? No, what? All of this is guesswork? No, this is not guesswork.
Shot them down. Theory is guesswork.
No, this isn't theory. This isn't guesswork. Okay, this is not guesswork any more than anything else you think. Any normal fact. You're sitting in a chair, more or less guesswork. But at that level, what I've said is true. Okay, what part do you think might be guesswork? I mean, because there's always stuff that hangs out that over time, in terms of data and fact, that changes over time, right? I mean, Newton's theory of gravity was guesswork in the sense that Einstein came up with something better. So you want to call Newton's theory of gravity guesswork? If you do, then I'll agree with you that this is guesswork. But anyway, what were you saying?
So I'm losing my train of thought.
Sorry.
Does that mean, is there a possibility that some part of the universe, maybe the opposite or somewhere in a corner, there might be some place that we would call dead, as opposed to this forming alive?
Are there parts of the universe in the corner over there, the universe, which is somehow or other dead, versus over here, which is like alive? And so the answer is yes, of course. Is everything you can think of. This is what the laws of physics essentially say. If it isn't against the laws of physics, then it's true. In other words, anything you can imagine that doesn't violate the laws of physics is true out there. So if you're saying there's some region of the universe that's dead, I'm going to go, yeah, you're right. There, for example, the universe is made up of places where there are stars, and those stars are in the things called galaxies. And the galaxies are part of a thing called a filament, where it's like little Christmas ornaments on a string. And those galaxies form a string called a filament. And the filaments are draped around trees, and they create clusters of filaments. And the filaments are draped around the trees, and guess what's between the filaments? Nothing. They're called voids. So the universe is filled mostly with voids, which you would call dead, if you want to call, because there's nothing forming there. There's not enough gas. There's gas there, but there's not enough. The gas is so diffuse that there's no possibility that gas is ever going to form stars. So it's dead. The gas sits there forever and does nothing forever. Okay, is that dead? Because if you want to call nothing happening dead, yes. Molecules don't die. The molecules that I'm breathing in and out were breathed in and out by the dinosaurs. You know, I'm made up of stuff that was used to be inside of a different star that blew up. Those molecules didn't die. So what do you mean by dead? Inert.
Not forming.
Not doing anything special.
Not changing, forming, evolving.
Right.
Exploding.
Well, but again, everything as long as something is above absolute zero. When absolute zero is when nothing's happening. Absolute zero says everything stops moving. There is no motion. There is no atom here goes to there, because that would mean that it had heat. So absolute zero is nothing. Anything above absolute zero means that a given molecule, any molecule in the universe, anyone you find and identify is going someplace and has a certain temperature. So if you think of each molecule having a mind of its own, each molecule is in the universe is doing something, and therefore the universe isn't dead. The question is, are they getting together to have a party, which would be a cloud, which would eventually form a star? Are they doing any of that stuff in the void? The answer is no, they're not doing any of that stuff in the void. So it's dead. Yes?
I read that we're running out of helium.
You're read that we're running out of helium. So that is probably not true. What is true is that we're running out of the helium that we stored during World War II, that we put in vast tanks so that we could save it for a national emergency. What's true is that the helium that they put in those tanks is being used up because we are not worried about helium anymore. So we get it out of the ground. When the Earth was formed, and then there was hydrogen and there was helium and the other stuff that the Earth is made out of. Well, the stuff that comes out of the ground is stuff like, has a lot of hydrocarbons, which is hydrogen, and with that gas is also helium from the creation of the Earth. So there isn't any more helium being produced on the Earth. That is true. But I would only worry about it when you tell me they're not finding any more natural gas. If you tell me they're not finding any more natural gas, I would agree with you, we're running out of helium. But since we're not running out of natural gas, we're not running out of helium, okay? It's just we're depleting the tanks full of helium that we accumulated over decades. I saw another hand, yes?
So when you talk about the void, is that absolute zero?
No, the void is close to absolute zero. But it turns out the universe is 3 degrees above absolute zero, everywhere. Everywhere. The universe has a temperature. Because when the universe was little, in the sense of 3.8 billion years ago, when it was just a baby, this big, whatever this big means, it was very hot. And when you expand something that's very hot, it cools off. So the bigger you make something that's very hot, the cooler it gets. When you make the thing as big as our universe out of something that was a big bangy type of thing, then the universe cools down to exactly 3 degrees above absolute zero. The universe is that temperature everywhere. Everywhere you look. That's the funny thing. Because
70 centigrade.
what?
Minus 270 centigrade.
Minus 270 centigrade. Yes, by the way, when I talk about degrees in this class, from time to time, I mostly talk about it in centigrade, not Fahrenheit. Otherwise, I should have said 6 degrees above absolute zero. But nobody in science, in physics, talks in Fahrenheit. The only time we talk about Fahrenheit is the temperature of the Earth for people who live in the United States, and the temperature of the sun for people who live in the United States. So even the temperature of the sun is quoted as 5,000 degrees, but it's Kelvin, which is not like centigrade, not Fahrenheit. And by the way, there's another thing. Fahrenheit and centigrade, they're different by a factor of 2. In other words, 2 degrees Fahrenheit is 1 degree centigrade, more or less. It's 9/5, but it's more or less. So 5,000 degrees on the surface of the sun, centigrade, is 10,000 degrees Fahrenheit. Except that there's something I again lied to you about the centigrade. We're not talking centigrade. Nobody talks centigrade. Marianne over here raised the point, the sticky point, that we don't talk centigrade, we talk about something called Kelvin. Kelvin, 0 degrees Kelvin is absolute zero. But absolute zero is minus 273 degrees centigrade. I never say, because what? Absolute zero is minus 273 degrees? No, that would confuse you. So I say zero and we leave it at that. But when we get to room temperature, it's about 300 degrees Kelvin. And and room temperature 72 degrees Fahrenheit. But if we were using something the same way we used Kelvin, then there's this thing called Rankine. And it's 470 something degrees below zero Rankine to get to absolute zero. Those are things you don't need to know. So instead of telling you any of that, which I didn't tell you, forget I just said any of that, just go with absolute zero and then hotter, okay? And if you need to know something specific that relates to you or your human condition living in the United States, we can talk Fahrenheit. But we'll never talk centigrade really, because we're always talking Kelvin, and we're never going to talk Rankine ever in this class. Who even knows that? Do you know, for example, that the mass of this water bottle is 1 kilogram? The weight of this water bottle is 1 kilogram. The weight of this, that's in the English system, the weight of this in the, and that's in the metric system. The weight of this in the English system is like 1 pound. But the mass of this in the English system is 1 slug. Slug, have you ever in your life, you're all over 70, some of you over 80, some of you over 90, have you ever heard the word slug applied to mass? That is our system. That is our system, okay? Really. So we're going to talk Kelvin in this class, and I'm never going to say it again, except the absolute, the temperature of the system, of the universe is 3 degrees above absolute zero Kelvin. Okay. Any questions about this diatribe of mine? No? Okay. Right. So that's. Should I play this a little bit longer? See if they go any further with this. So this is the our nearby clouds of gas star-forming regions. Now we're coming in from a different angle to see other star-forming regions, other gas clouds. But the culmination of this will be when they pull out. So there's, let's see, the Lobster Nebula, the Cat's Paw Nebula. The Lagoon Nebula, which we'll all visit. The Omega Nebula, we'll visit these. These are just, they're very, very beautiful pictures. But this is the picture that was taken by Gaia, and you can see that it only occupies a small portion of the Milky Way, which is the point that I want to raise once again. Yes?
Is that an artist's rendition of those molecules of gas, or is that something near reality?
It's not an artist's rendition. What you do is you tell the software that when it reaches a certain density, okay, look like this. Now there is you can believe that there are human beings who sit there and say, please draw this as a circle, because don't go crazy here. So please make this one a circle, but this one, bumpy like it is, leave it the way it is. They can, but the software is basically doing it. There are artists involved in making it pretty, but so it's somewhere in between. So it's not really an artist's conception because the software did it first, and then you go in and you tweak it a little bit to make it a little bit more interesting. You add colors, for example. You say, I think I'd like to have this color because it would separate itself from that which is separate. So there's definite points of view involved.
Do you know what caused them to choose what color?
This is, we'll call this the universe, okay? And without explaining it further at this moment, notice that there's a region in red over there. And the reason that region is red is because we know that those things belong to each other. You can't tell that they belong to one another. But we can, and I can prove it to you, because all I have to do is this. And you can see that it belongs to the same area. And I could show it better, but so the color is designed to imply proximity. It can also be used to imply another characteristic. They could use the same color to imply age or what it's made out of. So there are choices that the scientists make to give you an information in color. They only use one thing. In this case, proximity to one another is the thing that they're using in this particular case. Yes?
Wouldn't it also be likeness?
No.
Likeness.
Not likeness. No, likeness can be whatever likeness means, but you can pick a thing. Likeness meaning they have the same age, they're alike in the same age. They can be alike in terms of the things that they're made of, the degree of heavier metals than hydrogen. Helium could be another characteristic. They could be age. It'd be another characteristic.
So likeness is accurate.
Except that it doesn't, what I'm saying is I'm going to use the word characteristic, you use the word likeness. It's the same thing. Something that, in that case, was proximity. That likeness quality was their proximity to one another. They're all in the same place. That's all they're doing. They're just giving you that. So the lectures in this class do work 1,000 times better when they are questions than when I'm just lecturing. I don't have as much fun. You don't have as much fun, I think. And the reason that I think this is terrific is because, and what I'm doing is interesting, is there's no other class in astronomy being given on the World Wide Web that is interactive. There are lots of people who tell you things. They tell you things a lot better than I do, and they do it in a much more organized fashion. I do it in a randomly, whatever comes up next in my head is what I say, and you ask questions if I said it wrong, and that makes it so much better than anything that can be found on the web. So as far as I'm concerned, this is your product, Yes?
I'm not happy with the explanation you gave about why that red situation was red, because there's all sorts of stuff going on nearby and not so nearby that should also have had specific colors, idiosyncratic colors, and also the distance. You need a different approach of the pictorial approach, or a different angle to let me know that this area was distinguished by distance that made it so similar or something, because it just seemed to me there's much of a muchness.
Okay, well, here's what I'm going to do for you. I'm going to give you that perspective. Okay, these are galaxies. I didn't want to say that because it's next week's lecture, but now we're zooming in, and now do you see it? Now do you see it as we zoom in?
Oh, so it's more three-dimensional now, so I can see that it's separate from the things behind it and in front of it.
Right. Now you can see that they belong together. Before I didn't really prove that to you.
Are the colors arbitrary or?
The colors are arbitrary. Colors are arbitrary. There's another graph that I make, which is this one, okay, which it contains, in this one, the colors are not arbitrary. This is a completely different set of data, same data more or less, done by a completely different person, and in this case, the colors are not arbitrary. They're done to relate another aspect of these things than their proximity to one another.
And
But
what is that?
I don't know. I hadn't studied this week. I used to know.
It's not constituency.
No, it could be age. It could be metallicity. I used to know why that was in fact colored this way, but and it's right there in my notes, but I forget. So
It's still arbitrary, though.
it's arbitrary, of course, just not proximity.
Right.
Is the thing that
Maybe
doesn't.
contrasting to show structure.
Maybe he's contrasting to show structure.
So to
That's called the
use
two mass data set. And when I publish this on the web, I will explain why 2-mass is colored differently than Tully, which is colored one way, 2-mass is colored another way. So Is everybody going to sign that sheet and circle it? Thanks.
Did you see on the Super Bowl this weekend, the Turkish Airlines, which I know existed, but advertised for the first time?
I usually fly Turkish Airlines, so.
Right,
Yeah,
yes.
yeah.
But, I mean, usually people aren't aware that they exist.
Yeah, they're a very good airline.
They're not bad.
Their airport in Istanbul is horrible because they just built a new one and named it after their dictator, Erdogan. And the problem with the airport is it's 5 times bigger than it should be, and it takes months to get from A to B. And they don't have hardly any moving sidewalks. It's the biggest airport I've ever seen, with the worst designed flow of traffic I've ever seen.
Horrible.
Yeah.
Yeah, I found Turkey problematic.
And I did see the Super Bowl in 4K, by the way. I got 4K pixels, yes.
Just going back to that whole discussion about
Voids.
could we just picture the universe as a pie? And let's, what I'm asking, might there be 1/4 wedge that has the nothing, as opposed to intermittent? If it's just intermittent, it's really all similar or the same. I'm asking, might there be one whole section that might be completely different than the rest?
Well, you can see there's a wedge there. You can see there's a wedge, right? There's wedges. But no, the answer is no, there's no wedge that's different from any other. We have lots of wedges because we take data in wedges. If you look this way, you got a wedge. If you didn't look this way because you couldn't afford it, you only bought this much time, then you got a wedge in the sky. But so the universe is filled with wedges of data that we've taken. You can see the voids. I was talking about voids. You can see them in this picture. Look, there's voids. See them? See the voids? Places where there are no galaxies.
What's
But what would
there?
account for that?
The universe likes to do that. The universe, if you put it inside of a computer and you let it play, the universe ends up looking like that. And then, of course, you just have to ask me, what did I put inside the computer that made it look like that? Okay, but that's another story. And we'll tell
So
it.
what's in the black spot?
Voids, nyaten. That is less gas than there was in the places where there is gas. That's all. It's not like there's nothing. There's never any place in the universe with nothing. There's just less and more. There's no, and if you want to find some place with nothing, you have to look really small. As soon as you make it bigger, you found something. Maybe this big, you definitely have something. Maybe this big, maybe you got just nothing. It's just a matter of definition. Okay, so see you next week. Everybody signed the thing? Good. Thank you.
You could give a speech tomorrow.